Okay, so today we're going to tackle the concept of absolute potential energy, escape velocity, and black holes. Sounds pretty cool. I think it is. And one thing I will say is there's parts of here where it gets a little bit confusing, and don't worry about that. When we get to the kinetic energy of an orbiting object, the odds of them asking that question on the AP test are pretty small, but it's still worth covering. Most of this will be relevant, especially the potential energy and escape velocity parts of this. Okay, so back in Unit 3, when we introduced the concept of potential energy, we said it's the energy of position. You can have an object in a high energy position or a low energy position. So if it can fall, it's got potential energy. But we said the trick is you get to choose what you're going to call zero. So I quite cleverly, I would say, chose a diagram in which I have three 1 kilogram objects all positioned at the exact same height above the floor of the room. But there's a table in the room that's 1 meter high, and the objects are 1 meter above that. So in this case, this object, if I let it go, it would fall 1 meter, and given the gravitational field strength is 10 newtons per kilogram, the object would accelerate at 10 meters per second squared. So what I'd end up with is mgh would give me a value of 10 joules for this case, right? So 1 times 1 times 10. But if I take that same object and moved it here, now it would fall 2 meters to the floor. So instead of having 10 joules of potential energy, in this case, I'm going to say it has 20 because it's going to fall twice as far. But then I go, well, no, no, no. I'm going to tie this thing to a string. I'm going to make a pendulum out of it. And everybody knows that when a pendulum passes through its equilibrium point, the lowest point, we're going to call that zero potential energy. Set that as zero. So look at this. It's in the exact same position in the room, but here above the table, I say it has 10 joules. When it's positioned over the floor, I say it has 20. But when it's tied to a string at the exact same height, I say it has zero. And all of them happen to be correct. But these are what we call relative potential energies. There is, in fact, a way of calculating what the absolute potential energy is. How much energy does it really have due to its gravitational position? Now, to understand absolute potential energy, gravitational potential energy, think of it this way: it's the maximum energy an object can acquire by being lifted against gravity away from a planet or a star. So as I move it away, it's going to gain potential energy. There is a maximum limit to how much energy it can gain, and it shouldn't surprise you. It depends on the mass of the planet. All right, so one way of thinking about it is if I take an object and it's at, say, Earth's surface, so it's 1 r away from the center of the Earth. At that point, the gravitational field strength is 10. So if I lift a 1 kilogram object 1 meter, I would get 1 times 10 times 1, I get 10 joules. Done this a million times, Mr. Simpson. Yep, we have. But let's take it and move it farther away from the Earth. Now it's 10 radii away from the center of the Earth. So it's 10 times farther than it would be at the surface. Well, gravitational field strength at that height, since it goes down as a square of distance, is now 1/100th of what it was. So now I get 1 times 0.1 times 1. It only has 0.1 joules. It has 100 times less potential energy for the same amount of displacement. I displaced 1 kilogram 1 meter in both locations, but in one location, it acquired 100 times less energy. And that's only 10 Earth radii away. Okay, so if I keep going farther away, it's going to get a lot smaller than that. In fact, if we were to make a graph of the distance between the two objects, so the test mass that's being lifted and the planetary mass that's being lifted away from, and the force of gravity between them. So this is force. So force goes down as the square of distance. This is the distance. So if I multiply force times distance, that's work. That's the change in mechanical energy. In that case, this is the amount of potential energy it's gaining. We're going to get a graph like this. And if I take this area, there's a finite amount of, and if you take calculus, you learn how to calculate that using, I think it's Taylor series, but you could calculate this area under the curve, and that would be the absolute maximum amount of potential energy this object could ever have. So we're going to say that should be where, now here's, it takes a little bit of a mental jump here. There is a maximum amount of work that can be done against gravity. So there's a maximum amount of potential energy it can have. That should be what we consider its potential energy. But what we're going to do is we're going to say, since we're trying to figure out what to call zero, let's call that point zero. When it's out here, we're going to say that's zero. Therefore, anything closer is negative, because as I move in closer, I'm losing potential energy. So I'm going to assign it a negative value as I get closer. So the absolute UG can be found this way. So I say work equals force times distance. In this case, I'm going to say, I'm going to replace F with the universal gravitational force equation, and I'm going to multiply by R. So you can see this R cancels out one of these R's, and I simply get this. UG is just equal to GMM over R. Pretty straightforward, right? All I had to do is take force and replace it with gravitational force, and then my work equation gave me the potential energy equation. And we're going to put a negative here to indicate that because the far distant point is where we're going to put zero, anything closer is going to have less than zero gravitational potential energy. And that's a little bit confusing, but it's all right. Now, this part here, I'll just say, I just want to walk through this with you. This part here, I cannot imagine they would ever put on the AP test. But if you're interested, watch it. If not, just fast forward to the next part, okay? But definitely watch the part about escape velocity. But here you go. So, all right, let's just try this. Let's find the kinetic energy of an object in circular orbit. So it's got centripetal force, okay, which is, so we get this equation. And we're going to substitute gravitational force for centripetal force because that's what's causing the centripetal force. So we've done this a million times. And we're just going to go like we've done before, like we're solving for orbital speed, but we're going to stop when we get to v squared equals gm over r. And here's why. Because I want to find the kinetic energy. And remember, kinetic energy is 1/2 mv squared. So I write the kinetic energy equation, k equals 1/2 mv squared, and I'm going to substitute v squared with this value here. All right. Now it's going to, what happens then is I get the kinetic energy is equal to 1/2 g mm over r instead of r squared. All right. That's the kinetic energy of an orbiting object. Now, in circular orbit. Now, this part gets a little strange, but okay, so we're going to say, well, this is its kinetic energy. This is its gravitational. Remember, it's negative gmm over r. So in that sense, kinetic energy is negative 1/2 of this. So now I'm going to say, so it's negative 1/2 of the UG. So I'm going to say, well, if ME is K plus UG, then ME of an object in orbit is negative 1/2 plus UG, which gives me 1/2 UG. So what that tells me then is the mechanical energy of an object in orbit, in circular orbit, is equal to 1/2 of its absolute potential energy, which is just kind of a cool, beautiful thing. Okay, but now let's talk about escape velocity. So escape velocity, we said the other day, is if you go this fast, you escape and never come back, right? So if I have less than circular orbital velocity, I get this. If I have exactly circular orbit, I get this. If I have more than circular, what's required, the velocity required for circular orbit, I get this ellipse. And if I go 2 gm over r, or basically √2 times the circular orbital speed, it's never coming back, all right? So what that tells you then is √2v of circular orbit is the escape velocity for an object. But we can determine that value. We can derive that value using the potential energy equation. So escape velocity is the fastest an object can go due to its gravitational interaction with another object. So think of it this way. So if that's the maximum amount of work I can do lifting an object against gravity, so now I have an object that far away, I've lifted all the way up there and I let go of it, well, mechanical energy is going to be conserved. So when it falls back down, all of its potential energy is going to get converted to kinetic energy upon reaching the ground. So in a sense, the escape velocity determines the maximum amount of energy the object can have upon hitting the ground. So if we calculate that for Earth, what we find for Earth, it's 11.2 kilometers per second, 11,200 meters per second. If you're going that fast, so if I took an object all the way to the other side of the universe, and the only thing pulling on it was Earth's mass, the two objects interacting gravitationally, then when that test mass hit the Earth, this is how fast it would be going, 11.2 kilometers per second. Similarly, if I took that object and I shot it upwards from Earth's surface at 11.2 kilometers per second, then it would slow down as it moved away, but gravity would never get it quite all the way to zero. So it would approach but never reach zero, and it would never come back. It would escape from Earth. That doesn't mean gravity's not interacting with it anymore. It does, but it doesn't interact with it enough to slow it down, stop it, make it come back. So that's why we call it escape velocity. You basically escaped the clutches of gravity. It's not that gravity's not pulling on you. It's just that it's not pulling on you hard enough to make you turn around and come back. Now, we can derive the equation for escape velocity this way. We're going to go back and say, all right, so let's just use conservation of energy. There's no springs involved in gravity, so we'll just omit using US. So UG plus K equals UG plus K. I said this is initial, this is final. Initially, it has gravitational potential energy, and its final state is going to have kinetic energy, and I'll dispense with the negative here. We don't need it. So I'm going to say GMM over R, that's the gravitational force, is going to equal to 1/2 mv squared. So then I end up saying, all right, well, let's just multiply by 2. Let's get rid of our little m's. So I get 2 gm over r equals v squared. And when I solve for v, I get the formula for escape velocity. It's basically root 2 gm over r. Pretty cool. Now let's talk about what this has to do with black holes. Because most people, I think, when they hear about black holes, they're like, these things are cool. Now a lot of people think like black holes are like these evil shark-like things that move around the universe, sucking up stars and planets. But that's not what they are. All a black hole is a collapsed star remnant. So when a star is operating, the nuclear fires in its center part push it outwards. So it's basically, if I don't even use my hands, I have a diagram. Usually there's nuclear reactions here that are making this ball of gas hot, and so a hot gas expands. So there's an outward push of the heat expansion is balanced by the inward pull of gravity. But when these nuclear reactions cease, then gravity wins and the star begins to collapse inwards. And so the gravitational force becomes quite strong. And what happens in like our own star, it will only get small enough that all the atoms are touching anymore. It will be what we call a white dwarf. But if you have more mass than that, I think it's only like about 2.5 times the mass of the sun. What happens is as it collapses inwards, the weight of those atoms gets so strong they collapse inwards, and they basically become what's called degenerate matter. They have mass, but they have no volume. Their volume literally goes to zero. So that you have the mass of our sun, which is like 99.9% the mass of our solar system, and it fits into a space infinitely smaller than a grain of sand. We call that thing a singularity. It's a point, a geometric point in space that has mass equal to the mass of that collapsed star, minus however much of it blew away during its supernova phase. But it doesn't have any volume, so that means gravity gets the gravity field strength gets infinitely strong as I approach it. When a black hole is not this singularity. The singularity causes the black hole. The black hole is this region around it, this spherical region around it, where no light can escape from. So we call it black, so a black hole. And so the idea is if you cross this boundary, on this side of the boundary, escape velocity is less than the speed of light. At the boundary, escape velocity equals the speed of light. And if you're on the other side of the boundary, closer to the singularity, escape velocity is greater than the speed of light. Now, we don't cover special relativity in this course, but there are very solid reasons why an object, any object, even an individual electron, cannot be accelerated to the speed of light, much less beyond it. So any object that crosses this is never going to be able to escape from the gravitational pull of this. It can't escape because escape velocity requires you to go faster than the speed of light, and that's not possible. That's pretty wild. Now I love the name for this. We call this boundary where the escape velocity reaches the speed of light, we call it the event horizon. Events on this side can be known to the universe. Events on this side, don't know what happens there. So let's see how we find the event horizon of a black hole. So we say, well, escape velocity equation tells us that the escape velocity is simply equal to square root 2 gm over r. I'm going to substitute escape velocity with the speed of light, which is denoted by the letter c, as in equals mc squared. So the speed of light is equal to this. So now, if I square both sides, I get c squared equals this, and I'm just going to rearrange this for r, and what I see is the radius of a black hole's event horizon is going to equal to 2 gm over c squared. It's beautiful and simple and so elegant. So what would happen if the sun was to become a black hole? How big would it be? All right. So just so you know, the sun is huge, right? So I love this picture here. So if this is the size of the sun, this is the size of it. It gives you a sense of just how freaking big this thing is. And remember, it's 99.9% the mass of the entire solar system. So the sun's mass is 2 times 10 to the 30th kilograms, and the speed of light has to be 3 times 10 to the 8 meters per second, which, by the way, is a value worth knowing. Okay, it's a constant in the universe. If the sun could collapse into a singularity, which it can't, it had to be about 2.5 times more massive than it is. How big would that black hole be? All right. Now remember, this is the size of the world, so let's just compare it to that. All right, so I'm just going to say, well, the radius of a black hole is equal to 2gm over c squared. So I'm just going to substitute in the values for g, 6.67 times 10 to the negative 11th, the mass of our sun, which is 2 times 10 to the 30th kilograms, divided by the speed of light, which is 3 times 10 to the 8th. I'm going to square that value. And when I do all this, what I come up with is a radius of only 3 kilometers. If our sun was to become a black hole, that black hole's radius would be 3 kilometers. So I don't know. I personally find black holes to be totally fascinating. And if you get into relativity, you can start talking about the time dilation aspects of them. It's just so cool. And the thing is, they really do exist. We know for a fact that they do exist. Anyway, thanks for watching this, and we're almost done with the unit.